In studying comets, what you really want to do is get up close to one and look. So we want to investigate comets. So remember, the problem seeing a comet from Earth is we've got to look, and the nucleus, which is the solid part of the comet, is inside the coma, which is the head of the comet. That's the bright cloud of dust and gas surrounding it. Now, it's not super thick dust and gas, but it is dust and gas there that's blocking our view. And so for the large part, it's only been in recent years that we've been able to see comets far enough away from the sun before they, with bigger telescopes now, we can see comets far enough away from the sun before they've developed that dust and gas to make the head or the coma of the comet. So we've actually seen some evidence of the nucleus, but up until that's a fairly recent thing. So up until that point, we had never seen the nucleus of a comet. So that's why we wanted to see it up close. Now remember, the basic idea is that it's a dirty snowball. The basic idea of this dirty snowball model that Fred Whipple came up with is that the inside is this rock ice mixture, and then as the sunlight hits it, you sublimate away on the surface, and that leaves behind a lot of the dust. Okay, it also leaves behind some of the rocks, leaves behind organic molecules. And in fact, organic molecules seem to be the key, because in recent years, when we've seen the nucleus of a comet from very far away, it's kind of dark and reddish in color, which you expect from the UV degraded organic molecules. Impacts would occasionally hit and create little craters. Well, those craters would expose fresh material to blow out, and that would actually cause the material to blow out in little jets. Remember, you got these little craters. They're little cup-shaped things, and gas blowing out. That's exactly what a rocket engine looks like, the venturi tube of a rocket engine. Comets are notorious because they sometimes change orbits slightly. Asteroids don't change orbits, planets don't change orbit, nothing like this. I mean, yeah, the Garkovsky effect does move the asteroids a little bit, but nothing like the way comets do. They're notorious for speeding up, slowing down, shifting orbits inwards, outwards, and so forth. And so they don't change by an enormous amount, but they change enough that they're very difficult to predict exactly what they're going to do the next time they come by. And we've also seen occasionally in the head of the comet what looks like a jet or something spewing out. In other words, it's right where the coma is. It's brighter on one side than the other side, and sometimes there's even like spiral patterns that are spewing out. I've occasionally seen these things where it's pretty obvious there's something jetting out of the nucleus. So the idea would be that the sublimation would spew out preferentially along those craters and then shove the thing around a little bit. And so that was the idea. Now, of course, when it spews out, it's also going to be spewing out lots of little dust particles and small rocks and so forth. That makes getting close to the comet very, very difficult. Because when you get close to the comet, what's going to happen is that all these particles are streaming around with the comet. Now, normally your orbit's not going to really match the orbit of the comet, which means that those dust particles and things are moving at speeds that are many miles per second compared to your spacecraft. Now, even a dust grain or sand grain moving at that speed will impact with the force of a pretty large caliber bullet. So that means your spacecraft has to be armored against that. Well, 1986, Halley's Comet came by. And so, famous of all comets. And so, this seemed like a perfect opportunity to send spacecraft to go visit. Problem is, NASA was planning on sending a spacecraft, but the budget was cut at sort of the last minute, and we ended up not going. European Space Agency and Japanese Space Agency were both expected to ride along with us with instruments. All of a sudden, they were left scrambling to come up with something they could send themselves. And so Japanese Space Agency sent their own thing. Russia sent their own spacecraft. And the Kyoto spacecraft, which is a European Space Agency, sent their own spacecraft, the Kyoto. Now, this became kind of an international sort of problem because we had backed out after we'd already agreed to carry their instruments. Nonetheless, every nation in the world that had spacecraft sent something except the United States. And the Russian spacecraft actually got close to it and got bombarded by particles of debris from the comet, and the camera was damaged, and so it did not send back particularly good pictures. But this picture was the very first image sent back of the nucleus of a comet by the Giotto spacecraft. And so now we finally saw what this looked like. And sure enough, it's a dark nucleus that's only a dozen or so miles across, and these jets spewing out of gas and dust particles spewed out from the interior. So this was our very first view and was a major step forward. Over a decade later, the United States launched something called Deep Space One, which flew by Comet Borrelly. Now, flyby is really kind of a misnomer. It makes it sound like the comet sitting there and we flew past. Really what happened was the spacecraft was moving very slowly through space, and the comet came along really fast and went shooting past the spacecraft. Okay, so that's really what was happening here. But it was testing a brand new type of propulsion called an ion drive. That was really the Deep Space's main mission, was to test the ion drive, and they realized that during the test it would be passing not terribly far from a comet, so they flew by Comet Borrelly and got pictures of Borrelly. And again, Borrelly was just passing by, happened to be about the time that they were going to be doing the test of Deep Space One, and so they just adjusted the orbit so they just got in the path of Comet Borrelly. And so from Earth, Comet Borrelly looks like that. All you see is the coma surrounding the nucleus. And then as it was getting closer, then the spacecraft saw that picture, and when it got really close, it saw that. Now this is interesting because if we look at Comet Borrelly, it never got close enough to get really good pictures of it, and it wasn't really designed for that. But it does have craters and things in here. We have craters that do seem to be sources of jets here, and this narrowing region right here. So that narrowing region would explain something else that we sometimes discover, and that as these comets circle the sun after they've gone by several times, sometimes a piece of them breaks off and we have a mother comet and a calf or a daughter comet, and that smaller comet often dissipates. That would happen with something like this, where that little thing on the end breaks off and becomes a separate smaller comet. So that's an interesting sort of finding right there. Deep Space One kept going afterwards and passed an asteroid, the asteroid Braille, and gave our first up close view of that asteroid. Stardust spacecraft was launched in 1999 and flew in the path of Comet Wild 2. I know it says Wild, but it's pronounced Wild. So Wild 2. There's actually two of these comets, and so found two of them, and so it was going to fly in front of the comet, very close to the comet. So to armor the comet, on the front of the solar panels here and on the front of the spacecraft, there were these armored plates called Whipple shields, and they protected the solar panels and the spacecraft itself. And then sticking up above was this thing that looked a whole lot like a tennis racket that had in it a very soft gel that was going to collect samples of particles that were released by all these jets. Again, this is kind of what Comet Wild 2 looks like from Earth. You see the head of it. You see kind of a faint tail going off that way. And then as the Stardust got close, it saw that. And so it's kind of an oblong sort of thing. Unlike the other one, this has these super smooth features on here. Smooth indentations, not so much clear impact features, though they may have been impact features, but things have also been filled in, almost as if the interior of this thing was was not quite as solid and allowed material to flow or move into that area. And again, you have different kind of features on different parts of it that look different, suggesting that this comet is actually a more dynamic object than the other ones that we looked at. So this suggests maybe this is something quite a bit different right here. So this aerogel, this very loose gel, was actually captured some particles, and then the spacecraft flew back by Earth, and the container actually parachuted back down to the surface where it was recovered, and we had our very first samples of a comet. Now, what we found was, as we expected, a wide range of organic chemicals, including amino acids, mineral grains, but the weird thing was we found mineral grains that could only be formed at high temperatures. Remember, the comet comes from a very cold part of the solar system. What that suggests to us is that the propelid probably underwent substantial mixing of material in its early stages. Now that turns out to be very important because we had always assumed that asteroids had very little ice in them, but if this high temperature stuff got mixed to the outer solar system, that meant some icy stuff probably got mixed into the inner solar system, meaning that the asteroids and some of the things that made up the inner solar system had water in them probably. And so that was a huge step forward. That means not all the water in Earth came from comets. Some of it was probably native from some of the icy stuff that was mixed into some of the planetesimals in the inner solar system. There was very little processing of the minerals, meaning that even though we had these different sort of things, we had ices, that the ices never really melted and interacted with the material. So that means it stayed cold and frozen until basically we got samples. Now, one thing that was a little bit interesting is some of these organic molecules had very long organic chain links, indicating quite a bit of processing occurring there. Ultraviolet light breaks down the organic molecules, they recombine. This does so randomly, and in some cases you ended up with very long, complex hydrocarbons. Okay, again, this does not mean life, but it does mean that the chemistry that you need for life, some of the organic molecules do exist inside of comets.